page. For our electron configuration, let's pick, let's do a legitimately harder one, and just because we were just talking about it, titanium.
22.
Has 22 electrons. Where do we find that it has 22 electrons? On the periodic table, and on the periodic table is the number written in the upper right-hand corner. Okay? That would be the atomic number. In atomic notation, it would be written where? In the bottom left-hand corner. Okay? So we have to be careful on where we're looking and referencing these. So we've got 22 electrons that need to fill in. With the electron filling diagram, we could go through and just write this out. We could even memorize the pattern. It starts with 1s, then it moves to 2s, 2p, 3s, 3p, whoops. And actually, let's do a different color on that. 4s, 3d, and we could continue on. What goes after that? 4p.
32.
I haven't done electrons yet. 4p, etc. So we could write down the full list of all the possible orbitals all the way out based off of this chart. You could have it memorized. Okay? I don't recommend that. I think that's an awful, awful idea. Okay? The next part is now putting the electrons potentially in. When we talked about it in class, we started at hydrogen and just added one electron at a time all the way through. Okay? So if we've got our skeleton written out, we could go back and use the periodic table as a game of battleship. Remember our first two columns we called the S block. The scandium to zinc, so elements 21 to 30, those columns were known as the D block. Boron to neon were our P block. Yeah? Okay. So if we use that system, titanium is located in which block? The D block. So I would need to place the electrons for titanium in the D orbital. Okay? I could potentially go out to the 4D. We might say, well, isn't it in the fourth row? So wouldn't we expect 4D? We might, except we have to remember what's the deal with our transition elements. They are offset by 1. The first row of the transition elements is not the fourth energy, it's the third energy. Okay, that's why I conveniently stopped at 3D. Which column in the D block is titanium located in? The second block, which means the last electron goes into the 3D. There'd be 2 electrons in the D block. Everything now before that is full. So I could have memorized the S hold 2, the P hold 6, S hold 2, P hold 6, S hold 2, S hold 2. I sum all of the exponents and I get 22. It had better add up. If it doesn't, I did something wrong. Right? That meant that I knew all of those on how they filled. I memorized the electron configurations. I've never done that in my life. I go through the order that we just discussed. I start with hydrogen. I know hydrogen is the first energy level. It's part of the S block. I know I need 2 electrons in it. I'm now capped because I'd moved through helium to lithium. Whoops, as I write lithium. Lithium is in the second energy level, S block. Moving to the next element, beryllium, 2, 2p, continuing all the way through. And as I move column by column, I'd be adding 1 each time. Yeah? Both methods work. Notice I wrote down the exact same thing for both. Okay? You're responsible for getting that electron configuration in whatever form possible. Okay? Does that make sense for our electron configurations? Okay. For the sake of the next statement on this slide, we want to look at our valence electrons. Our valence electrons are ultimately a dictation or a result coming from Lewis bonding theory. Right? And when Lewis went through and developed bonding, he picked the simplest things possible. So he stayed in the second energy level. What's the issue with looking at titanium for our valence electrons then? I'm beyond 2 energy levels. Right? So let's back off of titanium, and not only that, I'm also into the D block. The D block is the biggest part that messes with our whole valence count. Okay? So for the sake of the class, let's change from titanium to calcium. Calcium would then have 20 electrons. Okay? How does that affect my electron configuration?
It'll be 4s2.
What do you got?
It's basically the same thing except without the 3D2.
I get rid of the 3D2, that's it. Okay? Now I want to know my valence electrons. The valence electrons are the outermost electrons. When Lewis went through and did his bonding, he said, what electrons should I be looking at? I know electrons are going to cause bonds because it's how those electrons are being shared that establishes a bond. Okay? Which of those 20 electrons should I be evaluating?
The 2 and the 4. The 2 and the 4.
I see what you're saying now.
4s2.
I will only look at the highest energy level. What is the highest energy level in that configuration? The 4th energy level. So I will only look at orbitals that have 4s in front. Conveniently, there's only one of them, and calcium has 2 valence electrons. That's it. Okay. Are we okay-ish with what's there?
If it has, say it has 2 4s in there, do you add the electrons together?
Let's
to find
pick
that?
carbon with 6 electrons. And actually, I want to take a note here. We had calcium with how many electrons? Valence electrons? 2 valence. Carbon has 6 electrons. Our electron configuration, 1s2, 2s2, 2p2, right? Okay. We sum our exponents. We're at 6. Everything works. If we look at where carbon is, it's in the second column of the p block in the second row. There's our 2p2. So far, so good? Okay. Valence electrons. We said the highest energy level. What is the highest energy level for the electron configuration? It's the second energy level, which then means how many valence electrons do I have for carbon? 4 valence. Good. Do we want another example? No? Oh, okay, I heard a yeah. The original questioner said no, but then others said yes. Okay, I heard xenon, no. I'll do aluminum. Let's do sulfur. Sulfur's total electrons, 16. Whoops, that's a 6. 1s2, 2s2, 2p6. Sulfur's in the third row, so I need to move 3s2, 3p. Sulfur's in the 1, 2, 3, fourth column, 3p4. Yeah? Highest energy level? 3. How many valence electrons does sulfur have? 6 valence. So far, so good. Okay. Is there an easier way to determine the valence electrons? Because if we go through and do this, we have to come up with the electron configuration every single time. That's going to kind of suck. Here we have to shift the periodic table. Calcium, we said, had how many valence? 2. Find calcium on the periodic table. Everybody got it? It's in the second column. The number at the very top of that is 2. How many valence did it have? 2. That was kind of cool. Carbon has 4 valence electrons. We find carbon. It's in the 14th column. That sounds a little bit weird, but what's interesting about that 14th column? If we looked at the Roman numerals, it would say 4. Just subtract 10. Why are we subtracting 10? Say that again. We're ignoring the 10 transition elements. Okay? So I can subtract 10 from that total of my column number 14, and I get 4 valence electrons for carbon. No electron configurations. Sulfur. We find sulfur. Which column is it in?
16.
The 16th column. I can ignore my 10 transition. And how many valences does it have? 6. No electron configurations. Right? Some periodic tables, for instance, did anybody print out the exam? Practice exam? No? If someone's got it, you got it handy? I just need it handy. You got it right here? Okay, let's take a look. Thank you. Except you didn't print the one page that I wanted, which is understandable. I need page number 2 in the practice exam. It should have a periodic table on it. Yes, take a look at your practice exam, and if you look at the column titles, they have the same numbering, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way up to 18. I can't count that fast. They also add, what else? It's underneath the numbers that say 10. What's under that 13?
B.
Under the 13? No, directly under the 13.
3A.
3A. We heard a lot of people shouting out Roman numerals. Guess what? The exam I gave you, no Roman numerals to worry about. You don't have to do that interpretation. It already tells you the number outright on it. You don't have to do any subtractions. You just look at the column label it's in. You now have your valence electrons. The periodic table tells you the valence electrons. Okay. How many valence electrons does xenon have? 8. Right? It's in the 18th column. Also, our 8A, I think, is the name of the row. Okay? The periodic table gives you all the valence electrons. Okay? And if you go through and calculate it using the electron configurations, you will find it's the same with one semi-caveat. We will ignore the d orbitals. Why? Lewis theory, again, centered on simple elements. We can apply that theory out to the more advanced elements, and it works in most cases, but we have to make some adaptations to it. Okay? Those adaptations you would do in 151. So you don't care about now. Just focus on your S and P electrons in your highest energy level. Okay? So, does that cover enough examples with electron configurations? Because you're my new questioner. Ish? No? Mary?
No, yeah, sure.
Good? Are we good with valence electrons? There's a couple hands. I guess you're going to go first.
Can you explain one more time how you're getting the entire row just by looking at the periodic table? The 1s to how you're getting all the way out without actually crossing it?
Okay, so let's start with carbon. Let's do carbon again. Let's clear all this out. Carbon has 6 valence electrons. I'm going to move through the periodic table 1 electron at a time. First electron would belong to hydrogen. Hydrogen's in the first energy level, S block, 1 electron. Helium, first energy level. Hydrogen and helium are a little bit weird. It's still officially S block, another electron. Condenses to 1s2. The next electron goes to lithium in the second energy level, S block, first electron. Beryllium, second energy level, S block, 1 electron, condenses to 2s2. Boron, second energy level, first column of our P block. Okay. Carbon, second energy level, second column of our P block, condenses to 2p2. You do it enough times, it clicks and you've got that thing memorized through practice. If you outright memorize it, great, that's fine too, but I would argue you should just use the periodic table until it clicks. Does that make sense? Another hand?
I was going to ask you if this PowerPoint was going to be on.
This PowerPoint has been posted to Canvas. The video will also get posted to Canvas in theory, by 7 o'clock tonight. Okay. I will try and dump it to YouTube while in office hours. It depends how busy I get. If I don't make it in office hours, I'll try and do it in my OChem lab. Yes?
Just for confirmation, the reason my helium isn't with just the hydrogen in the S block is because it acts more like a gas.
Hydrogen has a full outer shell. So if we looked at its outer shell, outermost electrons, it's just the 1s, right? It's full. That makes it look an awful lot like the noble gases. So helium, not very reactive. So we've placed it with the noble gases. Hydrogen, on the other hand, has 1 electron. It tends to act very similarly to lithium, sodium, potassium, rubidium, all that fun stuff. Okay? That can be confusing because we have to remember that delineation. So sometimes on a periodic table, what you will actually see will be a second section right here. And in that box, what are we going to put in that box? Helium. And we'll have a second box over on the other side. And what are we going to put in that box? Hydrogen. Why? Because we're trying to represent that hydrogen and helium have similar chemistries on both sides of the periodic table. Why do we not duplicate them? This says, well, why do we have 2 hydrogens? We don't. We have 2 chemical natures of hydrogen. Depending on how we want to classify it, we could classify it in either location. We typically classify hydrogen in that first block because when we look at hydrogen's reactivity, it typically carries a +1 charge. Helium typically carries no charge and doesn't react with anything, much the same as the noble gases. If I put it antisocial, if I put it underneath or above the alkaline earth, because it's 2 words, right? The alkaline earth in that second column, it has a similar electron configuration, but its chemistry doesn't match those. Okay? So it's just trying to offset, and we're coming up with the form that most appropriately approximates the reactivity of those elements. Okay? We talked about the S block, P block, D block, F block. That's what this image is showing from your textbook. Questions about it, or are you good with it? Okay. Now that we have it, we can also reference those Roman numerals. If we take a look at germanium, which I know isn't on this chart, but if we extrapolate from our periodic table and drop germanium on, how many valence electrons does germanium have?
4.
We can look at the Roman numeral, which is actually 4A. Come on, there it is. Or we look at the 14 and we just subtract our transition elements and we end up with 4. Either way, the number of valence electrons germanium has? 4.
What does the A stand for?
The A is there to delineate different from the transition elements. So it's A and B. Notice how they shift. The P block gets a hit first, and then we'd later move into the transition elements. That's why they're B's. Okay? Kind of, sort of? Good enough. Not a quiz, because we don't have enough time. So, reasonable density for francium given the elemental table shown. What would we do? Okay. We need to figure out the symbol for francium. Where is francium? It's FR. It's at the bottom under all of those. Okay, so what happens? If we take an average, that's not going to help us out. Because francium is at the extreme end of this. If we take a look, lithium to sodium goes up by plus 0.4. From rubidium to cesium, it goes up by plus 0.4, really. So to go from cesium to francium, which is also one step, what would be a likely guess? 2.2, 2.3. There's a reasonable guess. You're using the data that you have access to predict out. Notice I left potassium off. Why? It's annoying because the potassium doesn't match the trend. So I removed the data to make the question less confusing. Okay. How many electrons fit in one p orbital? 2. How many electrons fit in the d orbitals? 10. What the F? Okay. Read the question very, very carefully. How many electrons fit in one p orbital?
Oh.
In a single orbital, you will only have 2 electrons. Okay? If we changed question 2 to make that in the p orbitals, our answer now becomes 6. Yeah, it's not pleasant. Don't blame me. I think that's a bit annoying. I don't like that question, but it does show up, so I have to address it. Okay? Read your questions very, very carefully.
What was the original number 2?
D orbitals. So D orbitals would be 10. Okay? Did you want to memorize that? No, I wish we had a table that told us it. How many columns are in the P block?
2.
Columns in the P block. 6 columns in the P block. How many electrons fit into the P orbitals? 6. How many columns in our D block? 10. How many electrons fit in the D orbitals? 10. The number of electrons comes straight out of the number of columns in your blocks. How many electrons fit in the F block? Or sorry, F orbitals? 14, because there are 14 columns in the F block. Kind of, sort of? Why does atomic radius increase down a column? Back to this. Okay, one theory was we increase the number of electrons. Question 4, why does the atomic radius decrease from left to right? Left to right, what did you do to the number of electrons? You increased them, and yet, what happened with the trend? It changed. So we cannot say, as our explanation for why the atomic radius increases down a column, that it's the number of electrons. That does not work as an answer, because that answer does not also explain 4. Why do we get the atomic radius increasing down a column? What is the outermost electron for lithium? Because I don't want to ask electron configurations. Lithium is located in which column? Sorry, which row? Which row? 2. Which block? S. Which column? 1. Sodium. Which row? Which block? Which column? Potassium. 4. S. 1. Why does our radius get bigger down a column? You're placing the last electron into a higher energy orbital. Okay? It's not that we have more electrons, it's that our last electron is going to a higher energy. That is by definition further away from the nucleus. Okay? What happens when we go left to right? Let's move lithium to, yeah, we can do beryllium. It would be 2s2. Boron. 2p1. Carbon. It's a little bit weird on this, but be 2p2, right? So when we move left to right, where's the last electron going? It's going into a sublevel. What dictates our size? The energy level. Apply the rule that we had from Rule 3. We're going to the exact same energy level. What should happen to the size? Nothing. If the electron's going in at the exact same energy, it's not moving further or closer. It's going in at the exact same energy, which means there is no change in size. Okay? What else changes as we move left to right? Okay, the proton. So we start down a column. Here's our nucleus. My other hand, let's make, there we go. This is an electron. When I move to lithium, I go to a higher energy level. It gets further away, right? You can see that jump. When we move lithium to beryllium, 2s1, 2s2, 2p1, 2p2, all the second energy level, which means No change in the radius. What else changes, as Sean suggested? The number of protons, which means the proton starts to be, or the nucleus starts to become more and more positive, which means
It's gonna bring them closer.
it's going to suck the electrons ever so slightly closer. Right? So when we move left to right, the electrons are going in the exact same location. But because the nucleus is stronger, because we've also added a proton left to right, our electrons get sucked in just a little bit more.
Is there a word for that?
I like my word, sucked in a little more.
Okay.
Is there a science word for it? I'm sure there is. There always
It
is.
sounds like gravity.
Condensing?
I don't
It's
think-
not gravity.
It
It's
does.
definitely not gravity, but it's a similar concept.
Is
To
it kind
gravity.
of like
We should be
condensing?
like a fancy chemistry word.
There probably is. It probably has to do with electricity. Okay? So when we move left to right, we decrease because the electrons are going in at the same energy level and the nucleus is getting stronger. That's why we see the decrease in the radius. Okay? Ultimately, it is very hard to ask that kind of question, particularly in a multiple choice situation. So how might I ask it?
That's it.
In a short answer, explain to me what's going on with it. Okay? What could I ask in a multiple choice? Which of the following elements has the largest radius? Do you need to know why? No. What do you need to know?
Whether it does or not.
You just need to know the trend. How do you know the trend? Because you wrote it down on the exam at the very beginning of the exam so you don't have to think about it ever again. That's how you know it. You didn't memorize it and wait till you saw the question. Okay? So, there's our atomic radius. We've got the trend now on that. We'll move to ionization energy. Ionization energy is a bit of a weird one. It is defined as the energy required to remove an electron. So remember, what we're looking at is our first level, our second energy level, our third, our fourth, our fifth, our sixth, our seventh, and then eventually what do we reach? The vacuum. Okay? If I'm looking at the ionization energy, I want to know how much energy. Are you laughing that I just wrote BAC and not?
Yeah.
I appreciate that. I saw that. Okay. There we're taking the electron and I'm putting it up here. That requires energy. How much energy? Well, it depends on everything else. That would be the name of ionization energy. What happens if my electron, instead of being located there, was located here? I get less energy. So ionization energy might happen to mirror what? Kind of. It's going to go to the valence electrons. We'll have to use the valence electrons. Where are the valence electrons located? On the outermost energy level, or outermost circles. Okay? Those are the ones that also contribute to what? The size. Ionization energy happens to track pretty darn well with size. Okay? So, generally, ionization energy increases as you go from bottom to the top. Why? Okay. Bottom is at the 7th energy. Top is at the 1st energy. Okay. We would expect it to increase because we're actually going to a lower energy level. Conveniently, our periodic table doesn't correlate with energy nicely. Okay. We have the inverse relationship on that. Okay. In general, the ionization energy increases as you go from left to right across the period. Okay. Why would it increase? Think about the size of the atom. The atom got smaller as we moved to left to right, so it's going to require more energy to remove that electron because the electron's lower in energy.
That tracks.
Okay? So it tracks nicely. Anybody have any issues with those trends as written? You look at that and you're like, yeah, there's nothing wrong with that. I'm perfectly happy with it.
What's the exception?
How would you know that there's an exception?
Because there's an exception everywhere.
No.
In the gaseous state?
Fair enough. We could use in the gaseous state. There's a specific condition on when this is valid. And in general. Okay? In general, this is the observed trend. Is it always the case? No. Okay? Where we can run into this is we say, oh, well, we've got exceptions. There aren't exceptions when you understand why ionization energy works, and that goes back to the electron configurations. Okay? If we use the trends don't evaluate the electron configurations. They look at ballpark big ideas. How many times do we look at the electron configuration when we think about anything? Fairly rarely. It's a pretty nuanced division all the way down to the structure. So when we look at our ionization energies, we tend to see them increase left to right. So on this table, we're starting with our atomic number 1, hydrogen. We'd move to helium, and the ionization increases. Why does it increase? Helium is smaller than hydrogen, which means the electrons are closer to the nucleus. It's going to require more energy to rip them away. When I move left to right, hydrogen to lithium, to sodium, to potassium, to rubidium, to cesium, that's not left to right. Sorry, we just did left to right. For those of you that missed that, right? Hydrogen to helium was left to right. Yeah. What am I referencing when I say hydrogen to lithium? Down the column. Down the column, what happens to the ionization energy? It decreases. Why does it decrease? The atomic radius. The electrons are further or closer to the vacuum, which means it's less energy to make that jump. If we go through, you will see tons of little weird spikes in those. Okay? Those spikes are what some people like to refer to as exceptions. They're not exceptions if you evaluate your electron configurations. Okay? With that, unfortunately, I will have, well, I'm not skipping it. I think it's neat. Let's take a look at our first exception. What elements are happening within that box? Whoops, come back here. I don't want pale green. That box, what elements are we talking about within that red box? We're looking at beryllium to boron. Notice the ionization energy decreased. But that's left to right. It should increase. Why? What's the electron configuration for beryllium? Electron configuration. 1s2. 2s2. Okay. What is it for boron? 1s2, 2s2, 2p1. The ionization energy is talking about removing an electron. So for beryllium, when I remove that electron, what does its configuration become? 1s2. I'm removing an electron. 2s1. What happens to boron? 1s2, 2s2. It does not become beryllium. The electron configuration matches beryllium. Two different statements. Well, now it's inherently obvious what's happening, right? Why beryllium's is higher than boron. Everybody see it? I just had 3 people tell me, yeah, they understood that. Okay? Those 3 or 4 people would better explain to me why that's now obvious.
You ask the question if we see it, yes.
Do you? Okay, there you go. We see what's written there. Do we understand why beryllium's is higher than boron? No. No, okay, good switch. Good recovery. Way to look out. Okay. Beryllium starts full electrons, right? All its orbitals fully filled. That looks awfully symmetrical to me. What do we say about symmetrical people? They are beautiful. I don't want to bring in better. No judgments here, sort of. When I remove that electron, is it as symmetrical? No. So it was beautiful and it has now become
The beast.
not beautiful. Beast, that's a nice way to do it. Okay. That may introduce some other terms in the next question. What happened to boron? Boron had 1 electron in 3 orbitals in its outermost.
So it was a beast.
It was a beast. And what happened when I removed that 1 electron? It became beautiful. Someone comes down the street and gives you the opportunity. You are a beast. And they say, hey, I will hit you with a stick and you will become beautiful. You're going to be like, no, I don't want to do that. Okay? There might be a barrier to that, but you'll probably be like, okay, I'm game. Make me beautiful. Someone comes down walking down the street. You're already beautiful, or you think you're beautiful. Doesn't matter. Okay? Someone comes up and says, I got a stick. I'm going to make you ugly. What are you going to do?
Run away?
You're probably going to say, no, no thank you, don't make me ugly. It's going to require a lot more energy to make you ugly. Beauty to beast transition, not easy, higher in energy. Beast to beauty, lower energy. Your trend, your electron configuration dictates that. Okay? All of those little spikes that you see in there where you see exceptions to the rule all go back to Beauty and the Beast. I'm actually liking Beast. Thanks a lot for that. I appreciate that. Okay? That's what's happening within it. The trend is what you are responsible for. Why not getting the exceptions? Because that's a lot harder. You have to know your electron configurations. You have to apply 2 or 3 levels deep. Okay? Are you expected to know that? I just explained it. Yes. Yes, you are. But that's the higher echelon students. Students that want an A, you should probably understand and figure that out. Students that just want a B, accept that point loss. Students that just want a C, ignore a lot of it. Okay? So, we could go through and look at all the other ones. I don't want to do that, but you can apply them out. Your textbook doesn't mention electron affinity. Electron affinity is the reverse of ionization energy. Ionization energy was rip an electron away from the atom. Electron affinity is I'm going to shove another electron in there. The ionization energy makes the atom what charge? It will become positive. Ionization energy is removing an electron. All cases, we're looking at a positive atom as a result, because we've lost an electron. Electron affinity is the reverse. I take an electron and I shove it into the atom. Okay. Now it becomes negative. We can go through and look at trends within that. Again, not a big deal. Don't stress about the electron affinity. But the point that I want to get across with this is that if we compare the electron affinity to the ionization energy and do some mathematical mumbo-jumbo, we end up with, ignore the trend, electronegativity. Electronegativity is now effectively an average, depending on who calculated it and how they calculated it, the average of the ionization energy and the electron affinity. It is now the ability for an atom to take bonding electrons from another atom. This is no longer dealing with vacuums. Okay? I have 2 atoms near each other. Okay? One says, I don't want my electron, take it. The other one says, I love electrons, I'm going to rip it away from you. That allows us to see how the electrons are being shared between the atoms or not shared. That's how we come up with the different classifications of bonds. We can use the electron fudge. The word at the top of that screen, electronegativity. I always yell at people for screwing that up too, so now I can't yell at people. Electronegativity, okay, is the ability to share those electrons, okay, to take from another atom. Fluorine is the most, cesium is the least. There was a neat little question on the activity thing, right, the play posit, that asked you to rank bromine. I believe it was nitrogen, sulfur, and bromine. Okay, for electronegativity. I went back and looked at that, and most people got that correct. Okay, for those people that went through and answered, how did you get the correct ranking for nitrogen, sulfur, and bromine? Okay, so I'm hearing some arguments of you looked at the columns to establish this. So our trend says fluorine's the most, francium's the least. If I go through and compare sulfur to bromine, the thing they have in common is chlorine, right? Is bromine more or less electronegative than chlorine? So we're going down the column, right? So bromine is less electronegative than chlorine. Right? What can you tell me about sulfur? Sulfur is also less electronegative than chlorine. I found the thing that's common between those, because they're on the diagonal, and I'm using that to now rank bromine and sulfur. So if I take these two things and put them together, where is bromine with respect to sulfur? Chlorine is less, or sulfur is less than chlorine, bromine is less than chlorine. What is the relationship between bromine and sulfur? They're both less than chlorine. Which one's more? The hands up is exactly the response you should be getting. I have no freaking clue. The only way you get that answer correct is by looking at that table and looking up the exact values of the electronegativities. Okay? How many of you want to memorize the exact electronegativities? You probably don't want to. Okay? Was there a smart aleck in the back raising your hand? No? Okay. I'll make a test just for you. Okay? We don't want to bother to memorize those. Okay? We want to memorize just the trend. And even the trend, we only want to memorize for roughly 10 seconds. Because in that 10 seconds, what am I doing? I'm drawing this trend on my periodic table so I no longer have to memorize it. Yep, you are. That's because the periodic table has tons of information in it. Get it labeled out there. Okay? The question that I asked on the play posit was intentionally, it was a seed question to make you go, what the hell, I can't answer this question unless I look up these facts. Okay? So that you would then come to class, and when I said, are there any questions? You would say, hell yes, I have a question. Why did I get this question wrong? But then you all looked at the table and just looked up the answers. Okay, okay? Makes sense? When we're looking at diagonals, I can only ask rankings on the other diagonal. The other diagonal is fair game because that one you can match out. I will leave that one for you to go through and decide. All the practice on ranking electronegativities follows something on a diagonal. Okay? Chapter 4. There's everything you needed to know about Chapter 4. Woohoo! Chapter 5, same deal. Everything you needed to know about Chapter 5, all on the chart, or all on that chart. One of the things that we haven't discussed specifically yet is ionic charges. And I don't want to talk about it right now. We'll talk about it after the exam. Okay? So I won't ask questions about ionic charges on the exam. Electronegativity comes in again because it is referencing bonding. And Chapter 12 is all about bonding. Okay? So we've got different types of bonds, which I believe was in the slide, so we just want to kind of float through this. We've got ionic bonds and covalent bonds. There's more, but that's all you're responsible for now. Okay? Ionic bonds involve a positively charged atom and a negatively charged atom. That would mean we need to know their ionic charges, which we will talk about after this exam, next Wednesday. Okay? Ionic radii, again, goes back to the charges. I'll bring that back around for that after the exam. Covalent bonds is the important one. Okay? When we bring our atoms together, they will start to share electrons between them. That means the orbitals must overlap. Well, if the orbitals overlap, what happens to the internuclear distance? That was a really fancy word. The distance between the nuclei if our orbitals overlap. They get closer than the atoms themselves. So when we look at our distances, it shrinks. It is slightly smaller than the sum of the radii. That's it. That's it. Bond energy. That's another fun one I don't want to talk about right now. What I really want to get into is so that we have some practice with Lewis structure. Okay? These rules, has anybody gone through and read the textbook on Lewis structure? Are they the same rules as the textbook? No. There's a significant difference between them. Mine are better.
You said it in the.
Maybe.
Isn't that
Okay.
organic chemistry?
It really comes down to how you apply bonding rules when you move into organic chemistry. If you don't have to move into organic chemistry, you don't really care. You can pick whatever rule set you want as long as you get the answer right. I'm okay with that. Okay? Realize that your rules down here at the bottom start to add in and become more and more complicated the more advanced you are in chem. Okay? So you could see extra things here depending on which rule set you look at. What I've got up here is everything that you need to know for this course and this course alone. Okay? Shape summary. Once you've got your structures, you then have to use this chart or another chart like it to determine the shapes. Okay? So for instance, if I drew a structure H2O, HOH, what would the shape of that structure be? What does it look like?
A line.
A line. What shape close matches a line?
Linear.
Linear. So we might say linear. Unfortunately,
It's not.
that is a Lewis structure. Lewis structure does not apply shape. Okay? Lewis structure is meant to deal with things in 2 dimensions and just match atoms together and just work with that. If we want to understand something about how that molecule sees the world and where it actually exists in 3-dimensional space, we have to either build the model so that we can see it in 3-dimensional space, or we have to come up with some arbitrary, pseudo-arbitrary rules to define what that shape is. When we go through and look at water, what we will do, just like we did with the Lewis structure, is draw a box around the center atom. We will then look at each face of the box. Okay, so the top face. Do I have electrons there? Yes. So, I just say it has electrons. That's it. There are electrons. How about the right face?
Yes.
Okay. A line is just 2 electrons that happen to be in a bond. So are there electrons there?
Yes.
Yeah. Electrons. Electrons. Yes. So how many groups of electrons do I have around the center atom? 4. Groups of electrons? 4. The electron pair geometry for water is tetrahedral. Not linear, tetrahedral. Okay. What is its molecular geometry? So here it just says electron pair geometry. I care about the electrons, and I'm not saying there's any kind of different way to represent electrons. Well, is that true? Look at water. Are all of those circles with a check mark next to them have the exact same thing drawn in them? No. 2 of them have dots, 2 of them have lines. The lines represented bonds, bonding electrons. The dots meant not bonding electrons. Okay? So there is a difference. I have 2 different types identified up here. Because of that, I will now refine my analysis. And I will say I have 2 groups of electrons that are bonding. Or sorry, let's try this again. 2 faces that are bonding. And I have 2 faces that are not bonding. I could go back to my whole chart and say, where does that show up? Or I could realize I already established that this was tetrahedral. I don't care about anything above. I need to be looking within this bottom section. 2 bonding, 2 not bonding. The shape is bent. Did Lewis accurately represent the 3-dimensional model? No. It accurately represented the bonding within that model, but it doesn't accurately reflect the shape. Okay? The analogy that we can run with this, which will sort of work, okay? My arm, if you drew it, would just be straight out from my body, right? How about this one? If you drew it in 2 dimensions, what does it look like?
One shorter than the other.
One is shorter than the other, but they are both straight lines coming out from my body, right?
Yes.
Okay. What happens if we now turn?
Now you're a weird bird.
The straight one still is straight. The one that was shorter now clearly is bent. Lewis, when he drew it out as a straight line, is looking at it on that face. He can't see the bend. Until you turn the structure, you wouldn't know it was bent. Okay? That's why we need to apply these shape rules. Kind of makes sense? Okay. It is literally just apply the rules to get your shapes. Why do we call it bent? Because someone said that looks bent to me. Why do we call it linear?
Straight?
Someone said that looks straight or linear. Trigonal pyramidal.
Looks like a triple.
Somebody arbitrarily looked at it and said that looks like a triangle that's a pyramid. So they called it trigonal pyramidal. That's it. Okay? You could look at it and see a boat. I don't care. You still got to call it trigonal pyramidal because somebody already said that's what it looks like.
Holding science.
Okay? It is defined as that shape. Much the same way that if I point to the element Fe, you will tell me the name of it is iron. Why is Fe iron and not IR? Because somebody said it was. Yes, there's an origin behind it, but somebody said it, that's how it stuck, period. Okay? We don't have to go beyond that. Okay? Which gets us to our actual drawing of Lewis structures. Okay? I don't remember in the video how much of these I told you to go through and do, or it's shown as an example. I made you do all of them, but I didn't show all of them, did I?
Yeah. Except seven. I don't think we went over full charge, but I think we
Really? Well, that was kind of dumb.
So what are the ones that are actually
Okay.
important?
So when you look at those, all of those are important. When you look at those, which of those were you like, whoa, what'd you just do? Yeah. Negative charge.
all of them.
Okay? We can double back to all of them. That's fine. So I'm going to look at OH minus. Rule number 1, total of valence electrons. Oxygen has how many valence electrons? 6. How'd you get that answer so fast? It's the column number it's in. Hydrogen has how many valence electrons? 1, because it's the column number it's in. If I just looked at that, oxygen with 6 electrons has what charge? Neutral. It has 6 protons, well, 8 protons, but we're ignoring the first 2 electrons. Everything's neutral. Hydrogen would be what charge? Neutral. So if I take a neutral oxygen and a neutral hydrogen and I put them together, what would I end up with?
Neutrals.
A neutral OH. Is OH minus neutral?
No.
No. It has an extra charge. What is that extra charge? A negative. How did I get negatively charged? I had to add an extra electron. Okay? Adding it to hydrogen, I don't want to do that either. Okay? I want to account for the charge separate from the atoms. The charge says I am minus 1. This means I had to add 1 electron. How did it become negative if I'm adding something? The electron is negative. The sign will bite you in the butt every single time. Watch out for the charge affecting your totals. How many electrons need to go into my drawing? 8 electrons. Okay? I need to pick a central atom, step 2. Okay? As a general rule, the least electronegative is our central atom. I have 2 atoms, oxygen and hydrogen. Which atom is the least electronegative? Hydrogen. So I could put hydrogen as the central atom. That becomes problematic because it only has the ability to have 1 bond. A central atom needs to be able to reach out multiple places. So hydrogen is not the best as the central atom. In fact, it is never the central atom. So we will define oxygen to be our central atom. I will then scatter the rest of the atoms around it. I will put it to the right. I actually changed my mind. I'm going to put it down below. Does that change my answer? No. It's completely identical. Okay? The example I like to give for that is, what is my name? Mike. Good job. Now here's the tricky one. What is my name now? It should still be Mike. Just because I look different because I'm facing a different direction doesn't change the identity of who I am. Right? Next rule, add electrons to the most electronegative. What atom is the most electronegative here?
Oh,
The oxygen is the most electronegative because it is closest to fluorine. So I will start placing electrons on that atom. Rule 3 is the big delineator, the big difference between my rule and everybody else's rules. Okay? Defined as putting the electrons on the most electronegative. Period. If you do it other ways, you can still potentially get to the right answer, but where you run into problems is if you have to hit 6 sub 1 resonance. You are dead in the water if you do it any other way. Okay? So, we'll get to that. I will place 8 electrons around the oxygen. Notice, I am placing them on the faces of a square around that center atom. For those of you who watch the video, why are we picking a square?
Symmetrical.
A circle is symmetrical too. Triangle is symmetrical. Lewis's original theory was based off of cubes. What is the flattened version of a cube? A square. That's why we place them around a square. Which happens to give us how many electrons? 8. Which sets us up with, it's not explicitly stated up there yet, okay, the octet rule. Every atom needs 8 electrons around it. No more, no less. With one exception. Hydrogen. Hydrogen has 2 electrons. Okay? This again comes down to how we count them. So let's move on to the next part. We've got all of our electrons in, 8 electrons. I cannot add any more electrons. I will convert pairs of electrons into a line. When what?
they are next facing another atom.
When those electrons are between another pair of, or another atom. So in this example, I only have one line to draw. You will find other chemists will go through and show all of the dots as lines. Okay?
That's annoying.
It is exceedingly annoying because one of the things we need to do for shape is to differentiate bonds and not bonds. How do you do that if they all look the same? Okay? That tends to be a really old school chemist or old school classically trained. That's the only reason they do the line. Hopefully those people, cover up the microphone, hopefully those people die soon and we stop doing that because it's stupid.
That's been probably on YouTube.
It seems like we have extra electrons, because hydrogen's got the 1 and oxygen's got 6. So why did we
The charge.
Oh, because we added the thing.
Our charge accounts for the extra electron.
There's not 8.
Okay, so we're looking at OH.
We're OH minus, yep.
What happens if there's not 8?
Got it.
Separate issues.
So we drew OH negative.
We drew OH negative because that was our goal. We said I wanted OH minus, let's do it.
Okay.
Okay? We need to satisfy the octet by moving pairs. So I will now go through and look at each atom and say, does its octet or is its octet satisfied? It's called oct, like octopus, because 8. How many electrons around the oxygen?
8.
There are 8. 2, 4, 6. That line has 2 electrons. That's 8. How many electrons around the hydrogen? 2. I will double count those electrons to both atoms. Why do I count to both atoms? Because they're sharing. Those electrons are by definition associated with both atoms. If they weren't, we wouldn't have a bond. Okay? Hydrogen only has 2. Remember, hydrogen is our exception. We only have 2 electrons around hydrogen. We don't achieve the octet. Okay? Its octet, if you will, is only 2 electrons. So, do all of our atoms have octets? Yes. Then what do we do with step 6.1 with resonance? Nothing. There's no reason to evaluate it. We don't need it. Rule 7, formal charge is equal to valence electrons minus bonds minus non-bonding electrons. That is officially how you do it. I put a strike through on it because I wanted you to at least be aware of it. Okay? You're not responsible for calculating formal charge. You are responsible for noting that this molecule is formally charged. Since I've got a whole bunch of stuff drawn all over that, let's just redraw that. How do I make sure that when I look at that structure in black now, that it has a formal charge of -1? I just need to write -1. Where is that -1 or that extra electron located? That depends on stuff that is beyond the scope of this classroom. You are not responsible for it. So you don't care where it's located. Specifically, you just care that it's located in that molecule. How do we make sure that that -1 is affiliated with that structure? Brackets. Okay. That was an awful lot of effort. You will oftentimes see me do that. Not 7 minus 1, that's just the corner of the bracket. Does that make sense? So we good with that? We ready for a harder one?
Yes.
SO3. So, beginning to end, what are our valence electrons? Sulfur has 6. Oxygen has? Okay. No charge, so I have a total of 12 electrons, right? Why? There's 3 oxygens. I have to multiply that by 3. And I get 24 electrons now need to go into my structure. Central atom needs to be the least electronegative. Which atom is the least electronegative? Sulfur. Okay. I will now scatter the oxygens around the sulfur. Again, it helps to scatter them on the face of the square. So if you can remember that you have that square around there, we can draw in the oxygens. Does it matter which faces? No. It's just a rotation of the structure, okay, which will become tricky with this one. Next rule, add electrons to the most electronegative. Which one is the most electronegative? Oxygen. Which oxygen is the most electronegative? I don't accept all of them, but it's pretty close. Whichever one we want, because they're all the same. Okay. So I will start putting electrons around the oxygen. Notice the first pair of electrons I put in a position where it could share with sulfur. Why do that?
Because that's what we do.
We're trying to show a bond to the sulfur. So eventually I'm going to have electrons there. So I will start there. There's my 8 electrons. I can move to the next one. 16, right? Yeah, I did that right.
Yep. 24.
And 24, correct?
Yep.
So far, so good. Next rule, pairs into a line. Whoop, wrong line. This is where an eraser comes in handy. So far, so good.
Yes.
Rule 6, satisfy the octet. How many electrons around the topmost oxygen? 8. How many are on the rightmost? Bottommost? How many electrons are on the sulfur? 6. Is 6 equal to 8? No. Okay? So now we have to worry about our rule 6. We have to satisfy the octet by moving pairs. Okay? Step 1 that is wrong. Well, now sulfur has 8 electrons. What is wrong with doing that? It has 2, 4, 6, 8. Sulfur has 8 electrons. The total count jumps up to 26. I don't have 26, I have 24. I can't just add more electrons to the structure. So that is an invalid maneuver. Mary, because you were talking about it?
You were saying the ones from the oxygen to be made available to
Okay. So I will take a pair of electrons from the oxygen. Let's do that. Let me draw the pair a little bit darker, right? Top oxygen, that pair of electrons. I'm going to move those, put those on the sulfur. Does the sulfur now have 8 electrons? Yeah, cool. So now I'm done, right?
It's incorrect. It's not.
What do I have to do?
You have to put it on the line, the bonding line.
If I go back and now look at that top oxygen, what happened?
It's not balanced.
It doesn't have 8. I have to place that pair of electrons in a location where both the sulfur and the oxygen have access to it.
The bond.
I will place it between the atoms. I now have a pair of electrons between atoms. What can I do? Draw a line. Guess what I now have?
Everything satisfied.
Everything satisfied. 2 bonds to oxygens are single bonds. 1 bond to oxygen is a double bond because there's 2 lines. We're just counting the number of lines. So far, so good.
Yes.
Okay. Formal charge. Do I need to worry about formal charge?
No.
Nope. The structure said it was neutral. I don't specify any charges. You write that as your answer, you get 1/3 of the credit. This is rule 6.1. We have to satisfy the octet by moving electrons. This is the concept of resonance. I moved the electrons from the topmost oxygen. Did I have to move the electrons from the topmost oxygen?
No.
There were other sources. I could have moved them from the side oxygen. And I would have ended up with this structure. Okay. Or I could have removed them from the bottom, and I would have ended up with this structure.
So we need all possible permutations.
Okay. Are there any other permutations? There's plenty of other electrons, but they're coming from the same atom. Those don't count. We get 3 permutations, now we would get full credit. This concept is known as resonance. Okay. You're packing up, but we have a really important question that's probably going to come out of this.
So with where the oxygen is bonded to the sulfur, can you move those around? Is that part of resonance or no?
I don't understand your question.
Like if you were to take oxygen and move it to the left side of the sulfur with the bonding.
Oh, I see what you're saying. What if we drew the oxygen over here?
Right, is that
When
part
dealing
of
with resonance, you will achieve your first base structure, okay, before you start moving electrons around. That structure is now frozen in location.
Okay.
You do not move it again. It is now locked in that position. That skeleton can get copied however many times you need to move the electrons around. But you do not do any rotations, which is a part within this. We could say that this structure is the same as this structure, right? If I just took this and I just went whoop, doesn't count because then I'm moving the structure.
So the only thing that moves is the bonding.
The only thing that moves are the electrons,
The electron bonding.
which is what dictates your bonding. This means we get 3 structures for resonance. We have to provide all 3 to get full credit.
Why is resonance so important? Because wouldn't that all be just sulfur?
Why does resonance become so important? That's a really good question, and one that I will delay on until you take my OChem class. For the moment, you don't need to care about why resonance is important. Ultimately, what resonance is doing is dictates all of the chemistry that can potentially come out of that molecule. It allows us to predict a lot of information. Okay? That is Lewis structure. Follow the rules that I have outlined. It always works. Okay? Because I have roughly 30 seconds. Let's go through and draw real quickly what some of the other models would have shown. I believe your textbook says place the electrons around the center atom. What will end up happening is that you won't have enough electrons. Get something like that? Did I count them right? Maybe one more. And you might say, oh, the oxygen's missing, so I'll move this pair here. How many structures do you draw? 1. There's no reason to move that pair of electrons up here or over here. Resonance becomes hidden in that analysis, and you do not see how to get the other 2/3 of the points. Okay? That is why I address this issue at the top. That is why we move with those rules, because it sets up resonance appropriately. Resonance is hugely important for OChem. I'm really tired of spending 2 or 3 weeks in OChem reteaching everybody how to draw Lewis structures because your Gen Chem instructors screwed it up so thoroughly. Okay? And this doesn't have to do with our Gen Chem instructors at CGC. This has to do with every general chemistry instructor I have ever talked to. Okay? It is a really big problem within the field. Okay? With that, I'll go ahead and stop.